Hello everyone, my name is Yitian Chai from Shanghai Jiaotong University. Today I am gonna present our work, Cross-Domain Deep Code Search with Meta-Learning. The past few years have witnessed a rapid development of deep learning for software engineering, in which code search has been one of the most successful applications. Compared with traditional text retrieval methods, deep learning-based code search learns representations of code and natural language using deep neural networks, and thus has achieved superb performance. The figure shows the overall framework of deep learning-based code search. In the training phase, a bimodal deep neural network is trained based on a large parallel corpus of code and natural language to learn the semantic representations of both queries and code snippets. Then, a similarity function is employed to numerically compute the similarity between code and query vectors. In the search phase, the deep learning model is given a query from the user. It computes the vectors using the trained model for both the query and code snippets in the codebase. Then, it goes through the codebase by matching the vector between the query and each code snippet. Snippets that have the best matching scores are returned as a search result. A major challenge for deep code search is the adaptation of deep learning models to domain-specific languages. State-of-the-art code search methods are mainly designed for common languages, such as Java and Python. They rely heavily on the availability of large parallel data to learn the semantic mappings between code and natural languages. However, there is an emerging trend of domain-specific languages such as Solidity for smart contracts, where code search is also needed. Here is an example. A programmer asks the well-trained neural network for a source code snippet using Solidity to sort an array. Although the neural network is well-trained with a large amount of data, it can understand well what is Solidity. Despite the superb performance, deep learning models are often data hungry. That means the performance can be limited due to scarcity of data in specific domains. A key idea to solve this problem is the few-shot learning. Few-shot learning is a machine learning technology that aims to quickly adapt a trained model to new tasks with a small number of training samples. Since the deep learning models have already known how to sort an array in other languages, we can simply provide a few examples to adapt to the model for a new language. One typical way to achieve this goal is to apply the well-known pre-trained language models, where an initial program representation model is pre-trained on a large corpus of common programming languages, such as Java and Python, and is further fine-tuned to domain-specific languages, such as SQL and Solidity. However, simply applying pre-trained language models such as CodeBERT can be problematic. Different languages have different features and correspond to different representations. Parameters learned from each language can distract each other, resulting in a conflict in the shared representation. One well-trained language model is faced with downstream tasks and programming language data that has never been seen before. It will easily lead to fine-tuning poor fitting. Our idea to address this problem is that, instead of learning a unified representation for all languages, we can learn the good initialization of model parameters which can be best reused in a domain-specific language, and this can be implemented with meta-learning. In this paper, we propose CDCS, a novel cross-domain deep code search method using meta-learning. In addition to pre-training and fine-tuning, CDCS adapts a few-shot meta-learning algorithm called MAML to learn the good initialization of model parameters, which can be best reused in a domain-specific language. The workflow of CDCS involves 4 steps. We first pre-training the model with a large corpus of multiple common languages, such as Java and Python. Then we perform meta-learning to adapt the pre-trained code representation model to the target domain. Finally, fine-tuning the model on the code search task and evaluating it. The pre-training phase aims to learn representations of code and natural language from a large corpus of multiple common languages. Similar to CodeBird, we pre-train using the task masked language model. The model-agnostic meta-learning method is used to learn a set of initialization parameters so that the model can convert quickly in fine-tune. We perform meta-learning to adapt the pre-trained code representation model to the target domain. We employ a meta-learning algorithm named MAML, which is a typical algorithm for few-shot learning. The key idea of MAML is to use a set of source tasks to find the initialization of parameters, from which learning a target task would require only a small number of training samples. In the context of code search, this amounts to using large data of common language to find good initial parameters and training a new code search model on a small domain-specific language, starting from the found initial parameters. In the fine-tuning phase, we apply CDCS to the code search task. In the target language, we fine-tune the model on the code search task, which is also regarded as a binary classification problem. For a corpus of natural language programming language pairs, we create the same number of negative samples by randomly replacing natural language or programming language in the origin pairs. We assign a label to each pair to indicate whether the natural language is corresponding to the programming language in the pair, 1 for relevant, 0 for irrelevant. Finally, we perform code search on the target language. We select the top K snippets from the code base, based on their similarity scores predicted by the code search model. We evaluate CDCS by addressing the following 4 research questions. How effective is CDCS in cross-domain code search? To verify the effectiveness of CDCS in cross-domain code search tasks, we take Python and Java as the source languages and transfer the learned model to 2 domain-specific languages. We evaluate the accuracy of code search by CDCS in 2 target languages. The research question 2 is what is the impact of data size on the performance of cross-domain code search? As mentioned, one of the challenges of cross-domain code search is the limitation of data size in the domain-specific language. In research question 2, we aim to study the effect of data size on the performance. We vary the size of dataset and compare the performance under different data sizes. The research question 3 is how effective is CDCS applied on other pre-trained programming language models. Besides CodeBird, there are other pre-trained models that also achieve outstanding results in software engineering tasks. We wonder whether other pre-trained models can have the same effectiveness on code search when equipped with meta-learning. The research question 4 is how do different hyperparameters affect the performance of CDCS? In order to study the effect of hyperparameters to the performance of CDCS, we assign different hyperparameters to CDCS and check the impact on the performance of code search. The dataset for pre-training and meta-learning we used is from CodeBERT. We use the Python and Java data. The dataset for domain-specific language training is from other open-source work. We use the Solidity and SQL data. The Solidity is a contractual programming language of Ethereum. Its syntax is similar to JavaScript and is designed to locate Ethereum virtual machine. And SQL is a database query and programming language. We measure the performance of code search using two popular quantitative criteria on the test set, including MRR and top K accuracy. They are commonly used for the evaluation of code search tasks. We compare CDCS with the following methods: code search with pre-training, code search based on pre-trained model with natural language, within domain code search with CodeBERT. That means the language using for pre-training and fine-tuning are the same. Cross-language code search with CodeBERT. That means the language using for pre-training and fine-tuning are different. Here are the experimental results. Overall, CDCS achieves the best performance among all the methods. From the results in the SQL dataset, we can see that CDCS outperforms the baseline models in terms of all metrics, especially the top one accuracy and MRR, which are about 11% and 7% greater than strong baselines, respectively. The improvement is more significant in the Solidity dataset. We can see that CDCS substantially outperforms the strong baselines, especially in terms of the top one accuracy and MRR, which are about 20% and 18% stronger, respectively. We also present the performance of CDCS under different data sizes. We vary the size of training data from 0 to full data. As the result shows, CDCS outperforms the baseline model under all data sizes, which supports the significance of the improvement achieved by CDCS. In particular, we note that when the data size gets smaller, the improvement of CDCS against the baseline model becomes most significant. We also evaluate the effectiveness of CDCS on other pre-trained models, such as GPT-2. We evaluate the performance of CDCS GPT-2 and compare it with baseline models that are also based on GPT-2. We experiment with Python, Java as the source language and test the performance in SQL and Solidity. The table shows the performance of the various models. Clearly, CDCS GPT-2 outperforms all the baseline models. The MRR scores of CDCS GPT-2 are about 5% and 10% greater than those of the baseline model in the SQL and Solidity languages, respectively. This affirms the effectiveness of CDCS GPT-2 when equipped with meta-learning. Finally, we evaluate CDCS with different hyperparameters such as bench sizes and learning rate. The results show that larger bench sizes have little impact on the performance, while smaller bench sizes can affect the performance. and the performance is insensitive to the learning rate when the learning rate is lower than 1e-5. However, learning rates that are larger than 1e-5 have significant impacts on performance. In conclusion, in this paper, we present CDCS, a cross-domain code search approach that reuses prior knowledge from a large corpus of common languages to domain-specific languages such as SQL and Solidity. CDCS extends pre-trained models such as CodeBERT with meta-learning. It employs a meta-learning algorithm named MAML, which learns a good initialization of model parameters so that the model can quickly reach the optimal point in a new task with a few data samples. Experimental results show that CDCS achieves significant improvement in domain-specific code search compared to pre-training and fine-tuning counterparts. In the future, we'll investigate our method in more languages and other software engineering tasks. That's all of my presentations. Thanks for listening, and welcome to ask any questions.